The multiverse theory is an interesting concept in cosmology that suggests the existence of many, perhaps infinite, universes beyond our own. These universes may have different physical laws, stability, and properties. Imagine our universe as a bridge within a vast cosmic bubble, where each bridge represents a separate universe, possibly with different versions of reality. This idea defies our understanding of existence and has sparked the imaginations of scientists and philosophers. Evidence for the multidimensional theory often comes from quantum mechanics and some explanation of cosmic inflation. Quantum mechanics suggests that particles can be in multiple states at once, suggesting that all possible outcomes can create a separate universe. Cosmic inflation, the theory that describes the rapid expansion of the universe after the Big Bang, also lends credence to the multimedia theory. According to this idea, different regions of space could have inflated at different rates, resulting in patchwork universes with different characteristics. Some regions may be habitable, while others may be completely barren. This scenario is consistent with the notion that our universe is an example of a larger and more diverse cosmic governor. Although there is no direct evidence for multimedia, its implications are growing through theoretical research. Scientists are discovering how our understanding of fundamental physics ultimately relates to the multiverse. Ultimately, the multiverse theory sets the limits of what we know and invites us to ponder the questions of our place in the universe and whether another reality as extraordinary as our own exists beyond the horizon of our understanding. Line theory is an interesting and ambitious framework that aims to explain the fundamental forces of nature, including gravity, electromagnetism, and nuclear forces. At its core, string theory proposes that the universe's smallest building blocks are not point-like particles, but tiny, vibrating strings. The way these strings vibrate determines the type of particles they produce, just like the different notes produced by a guitar string. This innovative approach provides a unified description of all particles and forces that originate from one basic entity, the line. One of the most compelling aspects of string theory is its potential to harmonize general relativity, which describes gravity, quantum mechanics, and the theory that governs the subatomic realm. Thus, string theory not only provides insight into the interrelationship of these forces, but also suggests a deeper interrelationship between them. This combination could lead to a more complete understanding of the universe, from the largest galaxies to the smallest particles. However, string theory is not without its problems. One of the most important obstacles is that the theory works at a scale far beyond current experimental capabilities. The lines themselves must be incredibly small, on the order of 10 billionths of a trillion meters, making direct observation nearly impossible with today's technology. This lack of empirical evidence raises questions about the validity of string theory, since scientific theories require not only mathematical consistency, but also empirical testing. In addition, string theory contains a broad landscape of possible solutions, known as the problem landscape. The multitude of possible scenarios makes it difficult to predict which version of the string theory most accurately describes our universe. As physicists continue to explore the implications and implications of string theory, there is hope that one day it may provide a comprehensive framework that unifies all known forces and particles in one elegant theory. Until then, it stands as a testament to man's curiosity and quest to understand the cosmos. Gravitational waves are the most powerful and energetic processes in the universe caused by the periodic fabric. Imagine a stone dropped into a still pond. The puzzles spread outwards, creating ripples on the water. Also, gravitational waves are created when massive objects such as black holes or neutron stars collide or accelerate, sending out waves that travel at the speed of light. Although Albert Einstein first predicted them a century ago in his theory of general relativity, it took decades for scientists to confirm them. The fundamental principle of gravitational waves allows us to observe and study cosmic events that cannot be detected by traditional telescopes. While telescopes capture light from stars, gravitational waves offer a different perspective, revealing the unseen forces and motions of the universe. For example, when two black holes orbit each other and eventually merge, they create gravitational waves, even billions of light-years away. This new way of observing the universe opens up a treasure trove of information about high-energy phenomena and the fundamental laws of physics. In September 2015, the LIGO Observatory made history by successfully detecting gravitational waves for the first time. This landmark achievement confirmed a key part of Einstein's theory and heralded a new era in astrophysics known as gravitational wave astronomy. The consequences of this are profound. Scientists can now use these tiny particles, much weaker than light, to gather information about some of the most extreme and enigmatic objects in space. The discovery also sparks our interest in the evolution of the universe and provides insights into its basic structure. Observing gravitational waves helps us study the life cycle of stars, the formation of black holes, and even the early moments of the universe. As we continue to refine our technology and increase our ability to detect these waves, we can answer some of astronomy's most difficult questions, bringing us closer to understanding the mysteries of our universe. Time dilation is an interesting concept born from Albert Einstein's theory of general relativity. It describes how time passes at different rates, depending on the strength of the gravitational field. Near an object as massive as a black hole, time has a profound effect. This occurs because massive objects weave together the fabric of their surroundings. The stronger the gravitational pull, the slower the time to a distant observer. Imagine a clock close to a black hole, where gravity is very strong. To a distant observer in space, this clock seems slower than its own. This effect is most pronounced when approaching the event horizon, which is no longer a point of return to anything past it. The closer you get to the black hole, the more this time dilation increases. If someone spins around a black hole for seconds, their distant counterpart sees many different timelines. This brings us to the core of general relativity, which changes our understanding of time and space. Contrary to previous concepts that accepted time as a constant and universal measure, Einstein showed that time can be stretched, compressed, and even bent under the influence of gravity. Hence, the interaction between mass and the curvature of space affects not only motion and trajectory, but also the flow of time. The implications of time dilation are interesting, especially when considering the nature of black holes. When we observe these cosmic giants, we are not only witnessing the phenomenon of gravity, we are witnessing the order of time in a way that defies our understanding of reality. The dance of time and gravity at these extreme scales opens a window into understanding not only black holes, but also the fundamental structure of the universe. Cosmic inflation is a fundamental concept of cosmology that addresses one of the most difficult discoveries in our understanding of the universe and its unity. This theory suggests that shortly after the Big Bang, the universe experienced a very rapid expansion, growing rapidly in 1 second. This short but powerful period of inflation helps explain why the universe appeared on a uniform or uniform scale. Before inflation, the universe was hot and dense. As it expands during this inflationary phase, regions that were once close enough for thermal communication have moved farther apart. This rapid expansion explains why, even at great distances, regions of space share the same temperature and density. It effectively removed all pre-inflationary chaos, flattening the universe into an almost even background on large scales. In addition, inflation causes small changes observed in the cosmic microwave background radiation, a remnant of the early universe. These small variations are important because they served as seeds to form all the galaxies and structures we see today. They show that even though the universe is largely uniform, it has the small amount of disorder necessary for matter to accumulate, eventually leading to the rich structure we observe. In general, cosmic inflation provides a basis for understanding the initial conditions of the universe, and also provides a nice link to observed phenomena in cosmology. It shows how a seemingly chaotic beginning evolved into the stable, vast cosmos that we explore and marvel at today. This theory continues to inspire researchers as they unravel the mysteries of our universe's origin. Dark energy is one of the most intriguing and obscure concepts in cosmology. It is believed to make up about 70% of the universe, but we know very little about it. The discovery of dark energy came about in the late 1990s, when astronomers noticed that the expansion of the universe was not only continuing, but accelerating. This acceleration indicated that some force was driving the galaxies to their accelerating rate, a mystery known as dark energy. What makes dark energy particularly interesting is its negative connotation. While ordinary matter and energy attract each other through gravity, dark energy seems to have the opposite effect. It separates galaxies, pulling them apart over time. This has important implications for the ultimate fate of the universe. If dark energy dominates, we may be headed for a future where galaxies are receding from us, leaving a vast void in space. This scenario, known as the Great Cooling, suggests that the universe could have cooled dramatically as it expanded. Eventually, the stars will burn out, the galaxies will end, and the universe may become a dark, cold, and lonely place. This concept challenges our understanding of the cosmos and raises profound questions about its nature and potential end. Interestingly, the exact nature of dark energy remains a mystery. Scientists have proposed a variety of theories, ranging from the possibility of replenishing energy density to dynamic forms that may change over time. Understanding dark energy is essential to unraveling the mysteries of the universe, its past and ultimate destiny. As research continues, understanding this enigmatic force could change our cosmos and our place in it. Quantum entanglement poses a major challenge to our conventional ideas about distance and communication. Occurs when pairs or groups of particles are bound together, and the position of one particle immediately affects the position of the other, no matter how far apart they are. This means that if you measure one particle, even if it is light years away, you immediately know the position of the other particles. This phenomenon seems to permeate our everyday experiences. Traditionally, we think of data transmission as something that requires a medium and cannot exceed the speed of light. However, bound particles work outside of this framework. This chaotic situation was described by the physicist Albert Einstein as a strange phenomenon from a distance. The consequences of this are enormous, and communication between bound particles is instantaneous, limiting our understanding of causality and the limits of distance. Moreover, the mystery of quantum entanglement forces us to rethink the fabric of reality. If entanglement can be harnessed, it opens up the possibility of advances such as quantum computing and quantum cryptography, which rely on instant entanglements. Such technologies could revolutionize communication, enabling systems that are faster but more secure than currently available. Accepting the concept of quantum entanglement encourages us to think about the universe in a less linear way. This leads us to believe that the interactions between particles go beyond conventional boundaries, blurring the lines between space, time, and the essence of communication. These amazing interactions represent a journey of scientific discovery, showing us that our universe is more complex than we yet understand. Edwin Hubble's discoveries in the early 20th century changed our understanding of the universe. Before creation, space was static, unchanging, and infinite. Hubble, while observing distant galaxies, discovered a surprising reality. The universe is expanding. By studying the light emitted by these galaxies, he showed that their light shifts toward the red spectrum, a phenomenon known as redshift, as they move away from us. This suggests that the farther a galaxy is from Earth, the faster it recedes. This discovery was monumental because it showed that the universe does not appear to be a static entity. Instead, he adopted the concept of dynamic change on a spatial scale. The idea that galaxies are not stationary but are traveling away from each other provided the first evidence for what later became known as the Big Bang theory. This theory suggests that the universe started from an incredibly hot and dense point and has been expanding ever since. Hubble's discovery also has philosophical implications. It has prompted scientists and thinkers to rethink the nature of the universe and our place in it. What we live in is not a single, isolated space, but an ever-expanding governorate of galaxies, cosmic structures, and dark space. He shifted the focus of cosmology from a static universe to history, change, and the beginning of everything. In recognition of his contributions, the Hubble Space Telescope was named in his honor, allowing astronomers to delve deeper into the wonders of the universe. As we gaze into space today, we stand on Hubble's shoulders, and its founding eyes are eternally intrigued by the mysteries that await discovery in our expanding universe. Launched in 1999, the Chandra X-ray Observatory has made major advances in our study of high-energy astrophysics. It was designed specifically to study the universe in X-rays, a form of light that cannot be seen by humans but contains a great deal of information about space. By observing high-energy phenomena such as black holes, supernova remnants, and neutron stars, Chandra has shed light on aspects of the universe hidden in ordinary light. One of the most remarkable parts of it is the discovery of a large number of previously unseen objects. For example, Chandra has provided unprecedented insights into the behavior of black holes. Observations show how they devour nearby matter, producing powerful jets and X-ray winds. These processes help us understand the extreme physical conditions surrounding these enigmatic bodies and their influence on galaxy formation and evolution. Chandra's observations also shed light on the behavior of dark matter and dark energy, two of the most mysterious components of our universe. By studying the X-ray emission from galaxy clusters, scientists have been able to map the distribution of dark matter, providing critical information about its role in the formation of cosmic structure. This possibility enhances our understanding of how galaxies and clusters interact on large cosmic scales. In addition, the observatory played a key role in the study of the remnants of supernova explosions, which are necessary for the distribution of elements throughout the universe. By examining these remnants, Chandra has helped us understand the life cycle of stars and the processes that create heavy elements, from the formation of planets to the materials necessary for life. The Chandra X-ray Observatory continues to explore the universe's most energetic phenomena through its innovative contributions. The Apollo missions, a series of extraordinary space explorations by NASA, greatly increased our understanding of the Moon and paved the way for future space exploration. One of the most important discoveries came from samples collected during these missions. Astronauts brought back nearly 400 kilograms of lunar rock and soil, which provided invaluable information about the Moon's composition. Analyzing these samples allowed scientists to unravel the Moon's geological history, revealing that it likely formed from debris left over from a massive Earth-Mars-sized collision billions of years ago. Apollo also changed our view of the lunar surface and its formation processes. Through careful examination of the samples and high-resolution photographs, taken during the lunar landing, scientists have learned about the structure and age of different regions of the Moon. This information helped to support theories about planet formation and the evolution of the solar system. In addition, the collected data paved the way for comparative studies of surface rocks, leading to advances in the understanding of volcanic activity, not only on the Moon, but also on other celestial bodies. In addition, the Apollo missions expanded our understanding of the lunar environment. Surface experiments, such as seismometer deployments, have allowed scientists to measure lunar tremors and reveal details about the Moon's interior. These concepts suggest that, like Earth, the Moon has a solid interior consisting of a crust, a mantle, and possibly a small core. The discovery opened up a debate about the geophysical processes that formed not only the Moon, but also other bodies in the solar system. Beyond the Moon, the Apollo missions sparked a broader ambition for space exploration. The advanced technologies developed for these missions, including improved spacecraft design, life support systems, and navigation techniques, laid the foundation for future missions beyond our planet. Thanks to the know-how gained during the Apollo missions, humanity has headed to Mars and beyond, forever changing our understanding of our place in space and igniting the desire to explore the final frontier. The Hubble Space Telescope, launched in 1990, profoundly changed our understanding of the universe. Before Hubble, astronomers relied on ground-based telescopes, which were limited to Earth's atmosphere. This atmospheric interface blurred the images and limited the quality of observations. However, Hubble lives in the vacuum of space above the clouds, allowing it to capture incredibly clear and detailed images of celestial bodies. One of Hubble's most important contributions is its ability to reveal the diversity of galaxies that fill the universe. With its sharp field of vision, Hubble has been able to get an amazing look at galaxies of all shapes and sizes, from spirals and ellipticals to irregular shapes. This enhanced view challenged previous notions of galaxy formation and evolution, suggesting that the universe is a bustling metropolis of diverse structures, each with its own story. In addition to studying galaxies, Hubble also played a key role in understanding cosmic phenomena, such as black holes and galaxies. His observations were crucial in determining the rate of expansion of the universe, leading to a deeper understanding of the acceleration of the expansion. This discovery radically changes the concept of cosmic dynamics, revealing the mysterious dark energy that is the driving force of the accelerating universe. In addition, Hubble captured images of distant galaxies whose light is billions of years old. These observations allow astronomers to look back at the universe at different stages of its evolution. This perspective has deepened our appreciation of space, revealed its vastness and complexity, and awakened an interest in our place. The Hubble Space Telescope not only changed the way we see the universe, it also inspired generations to explore the mysteries beyond our home planet. The Voyager missions that began in the late 1970s changed our understanding of the solar system. Voyager 1 and Voyager 2 were the first spacecraft to study the outer reaches of our cosmic neighborhood beyond the known planets. One of their most remarkable discoveries came from detailed photographs and data collected from Jupiter and Saturn. These missions revealed a wealth of information about their atmosphere, complex ring systems, and many moons, including the striking surface features of Jupiter's moon Europa, which has since been considered a prime candidate for potential extraterrestrial life. Voyager 2 continued to explore Uranus and Neptune, providing unprecedented information on the distant planets. We discovered that Uranus has a spin axis that is unique among the planets. This unusual inclination causes seasonal changes in the long orbital period. Neptune has surprised scientists with its dynamic atmosphere and the fastest winds in the solar system. These findings challenged previous assumptions about the characteristics of these gas giants. and provided a deeper understanding of their formation and atmospheric processes. In addition to planetary discoveries, the Voyager missions have greatly expanded our knowledge of the heliosphere, the region of space dominated by solar activity. Voyager 1's interstellar journey allowed scientists to measure cosmic rays and the interstellar medium, revealing how our solar system interacts with space beyond. This groundbreaking work helped define the boundaries of our solar system and provided information about the nature and environment of interstellar travel, confirming that other star systems must experience similar physical phenomena. The success of the Voyager missions not only increased our scientific knowledge, but also sparked interest in space exploration. Their image of a pale blue dot millions of miles away makes us reflect on the planet's place in the wider universe. Looking to the future, the legacy of the Voyager missions inspires new missions that push the boundaries of human understanding and exploration beyond the solar system. The discovery of the cosmic microwave background radiation was a turning point in our understanding of the origin of the universe, providing the strongest evidence for the Big Bang theory. This radiation is a remnant of a time when the universe was incredibly homogeneous and hot and dense. It was first identified in 1965 by Arno Penzias and Robert Wilson, stumbled upon it while examining radio waves from the Milky Way. What they found was not just noise, but a lingering signature of the early universe. According to the Big Bang theory, the universe began as a hot, dense point about 13.8 billion years ago and has been expanding ever since. The universe cooled as it expanded, allowing particles to combine and form atoms. About 380,000 years after the Big Bang, these atoms could interact with light, capped with free electrons. This moment, known as recombination, allowed light to travel freely for the first time, creating a snapshot of the universe's infancy. The cosmic microwave background rays are essentially primordial light, now stretched to microwave wavelengths due to the expansion of the universe. Its uniformity across all observations indicates that it formed in a hot, dense state. Its temperature changes provide important information about the initial conditions of the universe and the formation processes of galaxies and large-scale structures. The tiny changes observed in this radiation are believed to be the seeds of all matter in the universe. Scientists believe the cosmic microwave background is a key component of the Big Bang model because it fits the theory's predictions. Its existence proves that our universe had a definite beginning and has been evolving ever since. As our instruments and technology improve, we continue to study and measure these cosmic signals, providing deeper insights into the history and fate of the universe and fueling our thirst for cosmic understanding. The discovery of pulsars marked a remarkable milestone in the field of astrophysics and was made possible by the development of radio astronomy. In the late 1960s, Jocelyn Bell Burnell and a graduate student named Anthony Hewish used a radio telescope in England to study quasars. During the observations, they detected regular pulses of radio waves coming from a certain region of the sky. At first, the signals were so regular that they jokingly nicknamed them "little green men," which could be signals of extraterrestrial life. After further investigation, these signals entered a new astronomical object called a pulsar. Pulsars are rapidly rotating neutron stars that emit radiation from their magnetic poles. Because these lights are so directional, they can only be detected when they pass through Earth like a lighthouse beam. A rhythmic pulsation occurs because the neutron star rotates at an amazing rate, some even completing a complete rotation several times per second, which makes the radio waves appear consistent and predictable. The implications of the pulsar discovery were profound. Not only did this provide evidence for the existence of neutron stars and strengthen our understanding of stellar evolution, Pulsars have also become a valuable tool in astrophysics. For example, their incredibly stable rotation allows scientists to use them as space clocks, helping to test theories of gravity and the structure of space-time. In addition, the study of pulsars in binary systems that orbit another star has opened up new avenues for investigating gravitational waves, which are caused by large-scale objects accelerating through space in the fabric of space-time. Radio astronomy was instrumental in discovering pulses, and thus enhanced our understanding of the universe. The discovery revealed the unusual life cycle of stars and provided tools to shed light on the complex nature of our cosmos. As we delve deeper into the mysteries of the pulsar, we understand both the fundamental laws of physics and the vast, dynamic universe that surrounds us.
Saturn is the second largest planet in the solar system, but most people know it by its visible rings. Astronomers regularly observe the gas giant, and its properties help us better understand the structure of the cosmos. Saturn is now well studied, and anyone can get detailed information about it. Size, mass, and orbit. Saturn has an impressive size, with an equatorial diameter of 120,536 kilometers and a polar diameter of 108,728 kilometers. It has an area of 427*10 square meters, -1, and a volume of 827*1014 cubic meters. km. Interesting fact: Saturn's parameters exceed those of Earth by the following parameters: radius 9.3, surface area 82, volume 765, mass 95. The average distance of the gas giant from the Sun is 1.4 billion kilometers. When the planet revolves completely around the star, the maximum distance increases to 1,513,783,000 kilometers, and the minimum distance decreases to 1,353,500,000 kilometers. Saturn's rotational speed is 969 kilometers per second, but this can vary depending on its position in space. A year on the planet lasts 10,759 days, 5 times longer than on Earth. Composition and surface. Because Saturn is a gas giant, its surface density is low, only 0.687 grams per cubic meter, cm. It consists of molecular hydrogen in a vaporous state saturated with helium. An interesting fact is that because Saturn's surface has a low density, the planet will not sink into water if placed on top of it. Beneath the first layer, metallic hydrogen and helium have accumulated in the liquid state. The substance also contains impurities of volatiles, but scientists have not yet been able to determine their composition. At the center of Saturn is a solid core with a radius of 12,500 kilometers and a rough surface. It is heated to 11,700 degrees Celsius and may be close to Earth's composition. Under the influence of high temperatures, helium near the core heats up and gradually rises upward, moving to the upper layer. Thanks to this, the surface of the giant receives a large amount of energy, which is 2.5 times more than the Sun receives. Atmosphere and temperature. The main substance found in the upper layer of the planet is hydrogen. It makes up 96.3%, helium to 3.25%, and other substances only 0.45% of the total volume. Scientists have found that among the latter are phosphine, ethane, acetylene, ammonia, methane, and propane. Above the surface there is a layer of clouds, divided into an upper and a lower level. The former is filled with ammonium crystals, and closer to the surface is a mixture of water and ammonium bisulfide. Clouds are exposed to ultraviolet light, which causes photolysis of methane. This leads to the start of chemical reactions of hydrocarbons. The atmosphere consists of lines extending closer to the equator. It is also possible to divide into 2 floors. At the top, the pressure varies from 0.5 to 2 bars, and the temperature from -173 to -113 degrees Celsius. Generally, these vary between 10 and 20 bars and between -3 and 57 degrees Celsius. Between the layers is a layer of ice clouds. Changes in temperature and pressure occur in the same way. Occasionally, Oval-shaped patches appear in Saturn's atmosphere that are whiter than other clouds. This makes them easily distinguishable on the surface. Scientists have not yet managed to explain their nature, but observations show that there is a pattern in the formation of spots. For example, when the summer solstice begins in the northern hemisphere of the gas giant, a large white spot appears in this area of the planet. There is a version according to which the formation of white patches is associated with electrostatic disturbances. Winds blow on the giant's surface with speeds that can reach 500 meters per second. It is the second largest in the solar system after Neptune. In the northern part of the planet appear currents with a wave structure, and in the southern part, jet. Fun fact, Saturn sometimes has storms that can reach Earth. One of the largest whirlpools, recorded by the Hubble telescope, was a hexagonal wind stream moving through the southern hemisphere. Its radius was 6,900 kilometers, and it made a complete revolution in 10 hours and 39 minutes. Saturn's structure studies have helped to show that Saturn is similar in structure to Jupiter and also consists of 3 layers. At its center is a rocky core. Its mass is estimated to be 10 to 20 times the mass of the Earth. It is surrounded on the outside by a layer of liquid metallic hydrogen about 14,500 kilometers thick. The top layer is 18,500 kilometers deep. It is made up almost entirely of molecular hydrogen. Because of Saturn's composition and the chemical reactions that occur there, Saturn emits large amounts of radiation into space. Scientists are still trying to figure out the reasons for the intense radiation. It is already known that inside the gas giant there is a Kelvin-Helmholtz reaction. Energy appears due to the large mass of the planet and the constant gravitational compression of such a massive matter. However, calculations show that this process is not yet capable of acting as a source of radiation in such quantities. This means that there are other processes occurring on Saturn that increase radiation. Heated helium streams are expected to be a source of additional radiation. Although Saturn's structure contains a solid core, most of the planet is composed of gas and has a low density. Orbit during a complete revolution around the Sun, the planet is on average 1.43 billion kilometers away from it. In comparison, Earth is 9.5 times closer to the star. Due to such an impressive distance, the planet completes a full revolution in 10,756 days. Interesting fact, it takes about 1 hour and 20 minutes for sunlight to reach Saturn. During this time, the planet travels a distance of 46,500 kilometers and orbits the star. The gas giant has the third largest eccentricity in the solar system, second only to Mars and Mercury. This parameter indicates how much the track deviates from a circular shape. In fact, this is the difference between the maximum and minimum distance from the Sun. Saturn's eccentricity is approximately 154 million kilometers, which is 400 times the distance between the Earth and the Moon. The planet's axis of rotation is tilted by 26.73 degrees. Because of this, the planet's seasons change. However, since Saturn is very far from the Sun, the difference in seasons is not as noticeable. The planet rotates around its axis fairly quickly, second only to Jupiter. A day on Saturn lasts 10 hours and 45 minutes. Because of the high speed, the shape of the planet is not round, but spherical, with a noticeable thickening at the equator. The atmosphere and surface of the planet are divided into visible latitudes, which also rotate, but at different speeds. This is because Saturn's upper layer is made up of gases rather than solids. Saturn's rings. Saturn has the most conspicuous rings of any planet in the solar system. They are mostly composed of ice particles, space debris, and dust. This is why they can be seen so well even from a great distance. At the moment, 7 rings of the gas giant are known. For convenience at the time of discovery, they were named with the letters of the English alphabet: A, B, C, D, E, F, and G. If you look at Saturn in a telescope from Earth's surface, only A, B, and C are clearly visible. Studies have shown that the 7 rings consist of thousands of smaller rings stacked against each other. At the same time, there are distances between the groups. The greatest distance between tires and B, it is 4,700 kilometers. An interesting fact is that the nearest circle of Saturn is 7,000 kilometers away and the farthest is 73,000 kilometers away. Although the total width of the tires is about 66.00 kilometers, they are less than 1 kilometer thick. The formation of the rings. The main version of the formation of Saturn's rings is that they were formed as a result of the destruction of the celestial body. About 4 billion years ago, a satellite composed mostly of ice was orbiting around the gas giant. Due to unknown factors, it came too close to the surface of Saturn, as a result of which gravity broke it into small pieces. The latter did not leave the planet's orbit under the influence of gravity, but rotating around Saturn around its axis, gradually formed rings. The approach of the satellite to the surface of the giant is only one of the versions of its death. It may also have collided with another celestial body. There is an alternative hypothesis about the presence of rings. It says that they formed with Saturn from the solar nebula. However, in this case, the ice forming the rings should be covered with dust and other particles, but it is crystal clear. Supporters of the hypothesis believe that the lack of external dirt is due to the regular collision of rocks during the movement. Satellites of the planet Saturn. Saturn has 62 major satellites with certain characteristics and 9 celestial bodies not yet named. More than half have a radius of less than 5 kilometers. But in the orbit of the gas giant there are also large satellites, the size of which can reach 5,000 kilometers. Most of the celestial bodies are named in honor of the Titans of ancient Greece. Among them are a group of inner satellites located between the planet and the rings. 1. My mass. The egg-shaped satellite is only 185,539 kilometers from the planet. It has a radius of 198 kilometers and a mass of 410 kilograms. My mass takes about 22 Earth hours to complete a revolution around Saturn. 2. Targeting. A spherical moon with a radius of 252 kilometers and a mass of 120 kilograms. It is believed to be the smallest satellite in the solar system that revolves on its axis. Enceladus has occasional geologic activity causing cracks and geysers in the southern latitudes. Rising water proves the existence of an inner ocean where life may exist. 3. Tethys. The radius of the moon is 533 kilometers. Its surface consists of craters and plains. 5. God. It is considered the largest inner satellite of Saturn. It has a radius of 556 kilometers and a mass of 121 kilograms. The large number of craters on the surface indicates the great age of the object. All inner satellites are composed mostly of ice. They may also have a solid rocky core. The outer satellites lie outside the E-ring. Most of them are composed of rocks and ice. How many satellites does Saturn have? Observations show that Saturn may have as many as 150 satellites, but only 62 of them are in orbit. The others are located at great distances and are categorized as irregular. It takes them several years to make a complete revolution around the gas giant. Exploration history. Since Saturn can be seen without a telescope, it was discovered by ancient people. Mentions of the planet are found in Babylonian sources. The Greeks named the gas giant Kronos in honor of the god of agriculture, and Ptolemy was even able to calculate its orbit. In 1610, Galileo used a telescope to discover the rings around Saturn, but mistook them for satellites. Sometime later, Christian Huygens discovered Titan and several other celestial bodies orbiting Saturn. Until the 20th century, astronomers discovered new satellites. Interesting fact: Christian Huygens was the first to discover and describe the rings of Saturn in 1655. When humans began to conquer space, several airplanes were sent to Saturn. In 1979, the Pioneer 11 probe flew past the planet and photographed it. In 1980, Voyager 1 arrived, followed a year later by Voyager 2. In 2004, the Cassini spacecraft began collecting information about the planet and Titan, and 2 years later discovered a new ring. The gas giant is now regularly observed in modern telescopes. When was Saturn discovered? Humans discovered Saturn in ancient times. It is one of 5 planets that can be seen in the sky with the naked eye. The gas giant was known in ancient Greece, Rome, and Babylon. Who discovered it? Although people have been observing Saturn in the sky since ancient times, its discoverer can be considered Galileo Galilei, who studied the planet with a telescope he invented and saw it up close. How did Saturn get its name? The ancient Greeks named the planet Kronos after the god of agriculture. The Romans decided to borrow it and named the celestial body after its predator, Saturn. The gas giant has been called that ever since. Age Saturn, like the other planets in the solar system, came into existence about 4.6 billion years ago. The hydrogen and helium in its composition suggest that the gas giant formed from a nebula. For the first 600 million years, the planet had no rings. Their research has shown them to be no older than 4 billion years old. How Saturn was born at first, the solar system was replaced by a huge cloud of dust and gas. At some point, it began to be affected by an external force. It could have been a wave from a supernova explosion or a collision with another cloud. This caused the cluster to rotate and gradually shrink. The energy accumulated in the center caused the protostar that became the Sun in the future. The remaining dust and gas began to swirl around the star and became a disk. The harder materials were closer to the center, and that's where the Earth group planets formed. The icy particles and gases are far away. They formed gas giants, including Saturn. Life on Saturn is unlikely given the conditions here. Since the surface layer is made up of gas, it is impossible to be on the surface. In addition, temperatures here can drop as low as -150 degrees Celsius. As you move toward the planet's core, where the climate is warmer, the pressure begins to increase. At depth, where the temperature rises above zero, it is about the same as at the bottom of the world's oceans. However, there may be life on Saturn's satellites. On Titan, for example, there are hydrocarbon seas in which simple organisms can live. Telescope observations, since Saturn can be seen in the sky with the naked eye, a telescope makes this task much easier. Even with amateur equipment, it is possible to get a large enough and clear enough image of the planet. You can find the gas giant in the southern sky. An interesting fact, because the rings also reflect light, the total visible surface area of the planet appears larger, making it easier to find. If you look at Saturn in a 60 to 70 millimeters telescope, you can see the rings and contours of Saturn. It is also possible to distinguish the colors of individual latitudes. For better detail, it is necessary to use fixtures with an aperture of at least 100 millimeters. Using a light filter doesn't hurt. Blue helps you see the rings more clearly, green shows details of the poles, and orange helps you see Saturn's center better. How long is the flight to Saturn? The journey from Earth to Saturn takes a long time. Pioneer 11 reached it in 5 years, and Voyager 1 overcame this distance in 3 years and 2 months. Voyager 2 approached the giant in 4 years, while Cassini took 6 years and 9 months. The last spacecraft to visit the planet was the New Horizons. It took him 2 years and 4 months to accomplish it. Such a big difference in travel time is due to the different composition of the ships and the routes chosen. The constellation of the Big Dipper. The constellation of the Big Dipper is one of the most popular constellations. Due to the great brightness of the star, it can be found in the sky even with the naked eye. Already in ancient times it was a landmark for travelers, but now scientists have managed to study the cluster well. The Big Dipper regularly becomes an object of observation, thanks to which astronomers make interesting discoveries and better understand the structure of the cosmos. What the Big Dipper looks like, description and characteristics. The Big Dipper is the third largest constellation. The area of the cluster is 1279.66 square kilometers, which is more than 3% of the entire starry sky. It revolves around Polaris, thanks to which at all times of the year it is above the horizon and is clearly visible in the sky. The Big Dipper consists of 7 bright stars that together form the shape of a dome with a rod. In Latin, the constellation is called the Big Dipper, and its abbreviation is Yuma. There are a large number of constellations in the vicinity of the cluster. This is not surprising given its impressive size. The list of neighbors includes a dragon, a giraffe, Veronica's hare, dogs, and both lions. Interesting fact. As Ottawa descends to the horizon in the fall, a legend spread among the Indians that in this way the animal prepares for hibernation. How to find Ottawa in the sky. Almost every constellation is quite difficult to find in the sky without special equipment. But thanks to the well-defined segment, finding Ottawa is not difficult. A person only needs to find this asterism and then the problem is solved. In late summer and early fall, the bucket is located in the northern part of the starry sky. For the best observation, it is recommended to wait until evening and leave the city, so that the light of houses and street lamps does not interfere with the light of the stars. Interesting fact: the north is easily determined by the position of the sun at noon. The star is now on the opposite side, in the south. In the fall, the asterism is located high in the night sky and is in a horizontal position. The stars that form it are so bright that the human eye immediately notices them, and the brain connects them to the objects sought by straight lines. As the Earth rotates around the sun and its axis, the position of the constellations visible from one point of the starry sky little by little changes. Therefore, in January-February, Ottawa gradually turns in a circle. The bucket tilts when the handle is below the horizontal position, and the location of the cluster itself gradually shifts to the northeast. In the spring, Ka is the hardest to find in the starry sky. During this time, the asterism will eventually invert, so the uninitiated may not notice it. The Big Dipper is worst seen in northern Russia. The area often has white nights that make it impossible to see the stars. And if you look at the constellation of the central and southern bands, you should remember that the scoop under this view is placed with the handle up. The Big Dipper in the representation of the ancients. The Big Dipper is considered one of the oldest constellations, as it was mentioned by almost every civilization that lived on Earth. The first information about the cluster can be found in India, where people called it Saptarishi, 7 sages. The name comes from the 7 main stars that make up the chariot. The latter was also noticed by the Chinese, who even determined the time by its position in the sky. The Greeks came up with a beautiful legend describing Ottawa. It is known that Zeus often paid attention to beautiful girls. Callisto, daughter of the king of Arcadia, was no exception. The wife of the god Hera learned about the plot and decided to take revenge. And so that the girl did not know the anger of the goddess, Zeus turned her into a bear and sent her to live in the sky, where she was completely safe. The Indians also saw a bear in this image, but according to them, the animal is made up of only 4 stars forming a trapezoid, and the handle of the ark depicts 3 hunters pursuing the beast. Elliot goes first and holds the bows, Mitzer carries the cauldron, and Bennett Nash Hospital brings a bush on his back arm to start a fire. Stars of the Big Dipper. The Big Dipper is made up of an impressive array of stars, but in his constellation, the bucket, there are only 7 lights forming a distinct shape. Thanks to modern technology, astronomers can constantly observe them and get the information they need. In addition to the 7 asterisms, the constellation contains about 125 stars. The human eye can only see 20 of them. Most notable are the 3 lights on the right side of the Dubmeric line. They form a triangle. In the lower right corner of the bucket is a similar figure consisting of bulbs, lambda, mu and psi. An interesting fact: in some cultures, the 2 triangles denote the hind and front paws of a bear. Also, several key stars are located to the right of the bucket, with only 2 luminaries hiding behind the horizon in Russia. And since in RF the constellation is always in the sky, by it local astronomers and stargazing people easily find the following objects. Asterisk Polaris, asterisk Cassiopeia, asterisk the constellation of Leo is nearby, asterisk the stars Capella and Arcturus, asterisk the constellation Gemini, asterisk the constellation Virgo. If you know which way these objects are located relative to the Big Dipper, you can easily find them. The variety of objects in the Big Dipper. Most of the objects of the Big Dipper are visible only in professional equipment. Only the Owl Nebula, labeled M97, can be seen in an amateur telescope. Next to it is the star Merak. Galaxies in that sector of the starry sky, where the Big Dipper is located, there are 1,500 galaxies of special interest to astronomers. And since the cluster is in the Milky Way, most of them can be seen in a professional telescope. The Cigar, Bode and Vertushka galaxies, designated M82, M81 and M101, are located at a distance of 12 million light-years from Earth. In addition, the former is considered one of the most beautiful objects in space, as its arms have a violet-blue luminescence, and the bright center is clearly defined and presented as a blue sphere. Superspiral galaxies have long, rounded tails surrounded by many bright objects. Astronomers compare them to fireworks because they resemble explosive fireworks. Next to the star Merak is the galaxy M108. Its center is hidden by dust clouds. They also absorb light that is about 12 meters away when viewed from Earth. Thanks to Phaeton's nearby illumination, you can see a Milky Way galaxy called M109. It is considered one of the most difficult objects to detect because the star often dims. Tracking the position of the polar bear, astronomers regularly discover new galaxies with unique properties. Its convenient position in the sky allows you to see even the most distant objects. Big Dipper, the owl in the fall. Since all cosmic objects are in constant motion, the Big Dipper is located in a specific area of the starry sky at different times of the year. In the fall, most of the lights are hidden from the human eye. Asterism, however, is an exception. Its 7 main stars, although not as bright in September and November, can be seen with the naked eye. In the fall, the Big Dipper is in the north under Polaris. The bucket is turned by the handle to the west. The constellation of Pleiades can be seen in the east, with Aldebaran shining closest to it. In the northeast are the main luminaries that make up Gemini. But not all clusters are visible in the fall. Virgo and Leo cross the horizon in the Russian region, and the Eagle is barely visible from behind the Big Dipper in the western region. In the fall, the brightest constellations in the sky are the Big Dipper and the Big Dipper *1 Taurus *twin. These clusters can be seen at night without special equipment. To observe other objects, astronomers use professional telescopes powerful enough to zoom in on stars and galaxies of interest. For example, the Hubble telescope can observe more than 1,000 galaxies located in the star sector of the Big Dipper. This ensures that researchers will not have to take seasonal breaks and stop working. Myths about the origin of the Big Dipper. There are several legends about the formation of the constellation. The most interesting and popular is the Greek one. The girl Callisto, daughter of King Arcadia, who was noticed by Zeus, has already been mentioned above. But there is another version of the myth. In his youth, Artemis often went to the forest to hunt, trying to find different game. In the assistant, he took exclusively beautiful young girls. Among them, Callisto possessed the brightest appearance. Her beauty attracted Zeus, and to win the favor of Callisto, the goddess passed herself off as Artemis. After some time, the girl gave birth to a son, Arcades. Zeus' wife Hera found out about her husband's deed and in anger turned Callisto into an ugly bear. Arcade grew up and became a hunter. And again the young man, who went out hunting, met his mother in the form of a bear. He did not recognize her and was about to shoot her with a bow, but Zeus intervened and turned them both into stars in the sky. Thus Callisto became Ursa, and Arcadius became Ursa. Since then they are always together in the starry sky, and because of the peculiarities of the place, both clusters seem to look at each other. And when a man has found one constellation in the sky, he can easily find another. An interesting fact is that because the stars Benetnesh and Dub move in the opposite direction to the rest of the stars, the bull gradually changes shape over the course of the year. When is the best time to see Ottawa? To see Ottawa on the territory of the Russian Federation, it is necessary to go outside the city, so that the light of streetlights does not obscure the objects in the sky. The best time to observe the cluster is March-April. Interesting fact, in the first weeks of April, Muscovites can see Ottawa at its peak of prosperity. During these months, the Big Dipper rises to its peak, and every day around 23 o'clock the stars reach their maximum brightness. Raising his head, a person immediately finds a bucket, and if he has at least amateur binoculars, he will be able to see not only the 7 main stars, but also nearby objects. The worst time to visit Ottawa is in the fall. At this point, the asterism loses its brightness, and without a telescope to observe the neighboring stars associated with the constellation, you cannot do without it. Orienteering with the help of the Ottawa bucket. Ottawa from ancient times has been a reliable reference point for people due to its good brightness. Depending on the time of year, experienced trekkers can identify key points and move in the right direction. Most importantly, the Big Dipper helps you find Polaris in the sky. If you mentally draw a straight line from the lamp to the ground, then with the help of this cross you can accurately determine the bottom. Interesting fact, in ancient Russia, the constellation was called the horse because of its characteristic shape. Ice cubes were considered a stick to which an animal was tied. Once you know the location of north, You will immediately understand where the other directions are. South is behind, west is to the left, east is to the right. The stars Arcturus and Spica in the south help navigate through space. In the Middle Ages, sailors used them to pinpoint the correct course while on a boat in the middle of the night sky. The advantage of Ottawa as an attraction is that it occupies a large area in space. Even if observations are made in cloudy weather, there is a good chance that at least part of the col will be visible in the sky. This is enough to identify the north location.
The Moon is Earth's only natural satellite and its closest neighbor in space. Most likely, the Moon was formed when an object the size of Mars collided with our planet. The catastrophe occurred billions of years ago. It turned the Earth into a molten ball and put a huge mass of matter into orbit, which cooled and took a round shape. The crater ball now orbits around our planet, causing the oceans to ebb and flow. The Moon is just over a quarter of the size of the Earth. This makes it the fifth largest natural satellite in the solar system. The Moon has several phases. For example, new moon, full moon, crescent moon, first quarter, and last quarter. But whatever the phase, our neighbor is hard to confuse with any other space object at night, and sometimes even during the day. But imagine waking up at night and seeing that the Moon looks different than usual. It seems brighter and more. However, in the case of a half moon, the changes are not as noticeable. You go back to bed without even realizing that Mercury has taken the Moon's place. The surface of Mercury, the closest planet to the Sun, resembles a lunar landscape. It's full of meteor craters. Mercury is no more than 2/5 the size of the Earth. It is, however, slightly larger than the Moon, and so the planet Earth has a greater influence. The nights are lighter, the tides are stronger. The lunar cycle, the period during which the Moon, or rather Mercury, goes through all its phases, is shortened by 14 hours. But overall, this substitution will not drastically affect the state of our planet. And what about Venus? What if our famous satellite replaced the third brightest natural object after the Sun and Moon? Venus is often called Earth's sister, as they are almost the same mass and size. In our sky, Venus would be the same size as the Earth observed by the Apollo crew from the surface of the Moon. The home star will be much brighter than the Moon. First, the planet reflects 6 times more sunlight. Second, it takes up at least 16 times more space. This is why nights on Earth become bright as early twilight. If you looked at Venus, you would notice fuzzy curls in its yellowish white cloud. Venus probably wouldn't be a satellite of Earth. Both planets would orbit around their common center of mass, and that orbit would be pretty weird. If Venus were moving at the same speed as the Moon, the planets would collide in the near future. Oh no, well, it's time to move on. If Mars were instead of the Moon. You're sure to spot it because of its reddish disk and the planet's size, which is twice the size of the Moon. You wouldn't even need a telescope to admire the unusual colors and dark spots on the planet's surface. And even if you don't pay attention to the red planet, you are bound to sense that something is off. Mars is half the size of Earth, but many times the size of the Moon. When a small spatial object is replaced by a larger one, it upsets the delicate balance. If you are unlucky enough to be on the coast when Mars replaces the Moon, you will have to evacuate quickly. The planet's impact creates strong waves that crash onto the coast like a giant tsunami. Mars reflects more sunlight than the Moon. Nights get lighter. Landscapes take on an eerie reddish hue. But you can use a telescope to admire Olympus the tallest mountain in the solar system. Mars is not large enough to radically change Earth's orbit. Over time, however, the two planets will probably begin to orbit around each other, forming a double planetary system. And because Mars is so close, traveling there becomes a reality. It's time to think more broadly. If Jupiter were to replace the Moon, Earth would cease to exist as an independent planet. It will become a satellite of the largest planet in the solar system. But there is some good news. In this case, people will have the opportunity to see the magnificent sky. Jupiter was incomparably larger than the Moon, and the giant striped ball stretched across the entire visible horizon. If there were time, you could admire the yellow, brown, red, and white clouds floating in Jupiter's atmosphere. Unfortunately, the gas giant's gravity would immediately cause earthquakes, volcanic eruptions, and tsunamis. The Earth's crust and mantle would begin to stretch toward Jupiter, and the Earth would tear apart. The planet would shrink and stretch in different directions by 90 meters. Unfortunately, Earth's speed is only 10% of the speed needed to stay in Jupiter's orbit. That's why our planet collided with the gas giant in less than 24 hours. But we're not sad. If Saturn had been there instead of the Moon, it would have been an unforgettable sight. The planet is more than 35 times the size of our satellite. The golden orb will be at an 18-degree angle in the sky, and the famous rings would stretch from horizon to horizon. Earth would be a little farther away from the gas giant than its satellite Dione, and since Saturn is so much more powerful than our planet, it would be Earth. Unfortunately, Earth's rotational velocity will not be enough, and we will collide with Saturn in a few days. But before we can enter the planet's atmosphere, we'll have to pass through its beautiful rings. They're made up of debris from comets, asteroids, and broken satellites. Yes, the journey ahead will not be easy. And don't forget that Earth has to revolve around Saturn's satellites, and there are 53 of them. What if the collision didn't happen, and Earth became the 54th satellite? Then the gas giant's gravity would cause violent tectonic changes throughout the Earth. The dear planet would be torn apart, and eventually there would be nothing left of it. Not a very positive result either. Both Uranus and Neptune are ice giants. They're about the same size. More than on Earth, but less than on Saturn and Jupiter. Both planets are covered in ice and have a beautiful greenish-gray color. If one of them replaced the Moon, the consequences would be the same. So, let's flip a coin. Okay, let's see what happens if you ever see Neptune in the sky. Neptune is 14 times larger than the Moon. The planet would look like a huge blue balloon. And not just during the day, but at night as well. You think Neptune is 15 times larger than the Sun, and you regularly experience solar eclipses. After the Sun disappears behind Neptune, our planet will go into total darkness for more than half an hour. Neptune's mass is 17 times that of Earth, and its gravitational pull is much stronger. So our planet would be a satellite. Yes, one more time. And it would orbit around Neptune at a slightly greater distance than its largest satellite, Triton. What's more, in this case, Earth could end up colliding with this cosmic object. But suppose we were lucky enough not to encounter any of Neptune's satellites. However, even without that, we'd have enough problems. Earth's waves will be 1,000 times stronger than the Moon's. Neptune's gravitational pull would not tear Earth apart, but it would warm our planet. Seismic activity would gradually increase, causing earthquakes and volcanic eruptions, and we would probably lose our internet. Use your imagination to draw two parallel horizontal lines. Now, connect them at any point in two different ways. A vertical line going straight up from the bottom line and a diagonal line. Which one is shorter? Of course, vertically. This is the shortest way to connect the top and bottom lines. And that's the most basic answer to our question. It's easier and faster to go straight up into orbit. The bottom is the surface of the Earth. Our planet is a complex mixture of all kinds of matter combined into an impressive mass, almost 6 sextillion tons. It's about 6 trillion billion, usually a big pile of zeros. Essentially, all of this mass acts as a giant magnet that, among other things, allows the Earth to retain what we all know as an atmosphere. The top line is the boundary of Earth's atmosphere. All of the above is planetary orbit and space, but the atmosphere itself is also full of matter. It's a mixture of gases that has its own density. When the shuttle is launched, the entire mass of this gas constantly compresses it, causing friction and slowing it down considerably. Going through a vacuum is like cutting through air, and going through the atmosphere is more like cutting through jelly. Grapes are like strawberries. It takes a lot of energy and strength to get through it, as you experience the tremendous pull of Earth's gravity. Airplanes don't suffer as much when passing through the atmosphere because they use its density to lift off the ground and maintain altitude. Two things that help them do this are engine thrust and the shape of the wings. The wings of an airplane cause the air in front of them to separate into two streams. Naturally, behind the wings the jets merge, but their shape makes the reverse flow faster. The faster the air moves, the more it loses density. This means that the flow under the wing is denser than the flow above. This causes the airplane to gradually rise upward. Essentially, the wings allow the airplane to glide through the air. Of course, this wouldn't be possible without the tremendous force pushing the car forward. That's what stakes are for. Just to get off the ground, the airplane has to reach a tremendous speed. The speed required depends largely on the type of airplane. 96.5 kilometers per h for light aircraft and about 241 kilometers per h for jets. A Boeing 747 needs just under 3 tons of fuel to take off and reach an altitude of 3 kilometers. This may sound impressive, but let's take a look at the space shuttle. The first thing that catches the eye is the beautiful short wings, which would be useless in a horizontal plane. On the other hand, more massive wings are useless in a space vacuum. They are also difficult to make strong enough to withstand gunfire. The small wings of the space shuttle serve only one purpose: to land safely so that the platform can be used for future missions. They would have to be large enough to prevent the shuttle from spinning uncontrollably as it descends through the atmosphere and delivers it to Earth, since no engines are used during descent. Spacecraft engines are completely different from aircraft engines. Aircraft engines need air from the atmosphere to operate. Apparently, shuttle engines don't need it because atmospheric air is hard to get in space. That's why the shuttles use rocket engines. To see what a rocket means in this case and how it all works, inflate and release a balloon. It spins until it runs out of air because it moves in the opposite direction to the air coming out. For takeoff, a rocket engine must create enough thrust and burn the required amount of fuel. In fact, the space shuttle needs so much fuel to achieve thrust at launch that it can't make do with just three engines. It would require 2 additional stationary rocket boosters and a separate huge fuel tank that is emptied during the final stage of the launch. And the shuttle will only be able to go into orbit with enough power. The shuttle's power with 3 engines and 2 boosters is about 3.5 million kilograms of thrust. To achieve this effective thrust, the external tank contains about 725,000 kilograms of fuel. And to control flight, those 3 engines must have a staggeringly complex design. Would it be possible to get the shuttle into orbit if we modified it to use the atmosphere like airplanes? Unfortunately, the answer is no. Even more fuel would be required to maintain the necessary speed at a distance from the diagonal launch trajectory. The fact is that even if the airplane reaches the upper atmosphere, the Earth still won't let it go. To leave the atmosphere, any object leaving the Earth must be fast enough to cross a point called escape velocity. This is necessary to overcome the planet's gravity and get the object into orbit. The rotational speed of our planet is 28,000 kilometers per hour. Obviously, this is well above the speed of sound and many times the speed of an airplane. Now, try to imagine an airplane flying at that speed and how much fuel it would need. It must also be strong enough to not break. The cost and complexity of the technology would be simply unrealistic. With the possibility of the shuttle becoming a thing of the past, scientists and engineers are looking for a better solution to reach orbit beyond it. One such idea suggests that in the future, people will be lifted into space in a huge space elevator. A space elevator is the concept of a huge tower that reaches an orbiting satellite, moving in time with the rotation of the Earth itself. The tower would have to be about 35,400 kilometers high, and it would have to be made of an incredibly strong material, carbon nanotubes. The platform inside the tower would have to be controlled by electromagnetic conveyors. The journey from Earth to the satellite takes only 5 hours. Such a megastructure would provide faster and safer access to space. However, carbon nanotubes were not strong enough to build such a large tower. Therefore, the search for the ideal material is still ongoing. Another project using a similar approach is called the space tram. The structure needed for the project is not that big, but it is still impressive. It is a vertical vacuum tunnel that lifts the shuttle by magnetic thrust. The air doesn't slow it down, and an electromagnetic force pushes through the tunnel, providing acceleration until the shuttle takes to the sky at near-space speeds. Such a shuttle would weigh less, since it wouldn't have to carry as much fuel, but there is still no word on how a human can withstand such acceleration. The crew can then be turned into a pancake. If such ideas seem strange to you, and they are, prepare for the latter. People can use airplanes to get into orbit. No, I wasn't lying to you. The car itself can't go into space, but it can act as a launch pad. Even better, right? A special aircraft with a wingspan of almost 122 meters and capable of reaching heights of more than 10 kilometers will be created for this purpose. Small shuttles launched from such an airplane wouldn't have to go through much of the atmosphere and would have an easier time overcoming Earth's gravity. Richard Branson is already working on this solution as part of the Virgin Galactic program, which takes passengers to the edge of space. Very often the world around us seems ordinary and commonplace. However, if you just look a little closer, everything turns out to be quite different. For a long time, we thought that our solar system was just one of many star systems in the Milky Way. There are rocky planets. Like everywhere else, there are also gas giants. But soon astronomy made great strides in studying and modeling the orbits of the planets, and it became clear that our system is extraordinary. And it's not because there is an Earth inhabited by intelligent beings, and it all started with Jupiter. Its orbit deviates too much from a circle. Its elongation, scientifically known as eccentricity, is 3 times that of the Earth. We know that it is very difficult to break the orbit of a celestial body when it has a large mass, and the more mass, the heavier it is. In the early days of the solar system, when the young planets were still emerging from the protoplanetary disk, they had smooth, circular orbits. Gravitational interaction with some object was required to achieve their elongation. Jupiter has 318 times the mass of Earth and 2.5 times the mass of all the other planets in the solar system. It takes huge gravitational interactions to expand that orbit that much. But with whom? What planet could have been so massive that it could have impacted Jupiter? Uranus and Neptune are also strange. By calculation, they must have been formed in their present location for longer than the protoplanetary disk could have existed. The only reasonable way out of this paradox is that they first formed much closer to the Sun and then moved farther away. But the big mystery of our system is Mars, and indeed all rocky planets. The farther a planet is from the Sun, the more massive it is. Finally, the farther away from the star this or that part of the protoplanetary cloud, the less matter in this part of the cloud moves outward under the influence of the radiation of the star and its wind. On the face of it, this is true. Mercury is 15 times lighter than Venus, and Venus is 1.18 times lighter than Earth. But Mars, this is where the pattern breaks down. It's 9 times lighter than our planet. Of course, some of the problems can be solved by saying that Jupiter's gravity has pulled some of the planet beyond Zemalea away from Mars. These are the small bodies from which the Earth group planets were formed. But calculations show that instead of Mars, there should have been a planet comparable to Earth, or at least half the size. This is not a matter of calculation or theory. Mars is located in the habitable zone of the solar system. If its atmosphere were at least comparable to Earth's, it would retain enough heat to make the Martian climate similar to Earth's dry climate. But in practice, today's atmosphere is 150 times thinner than ours, and gravity is too weak to support a denser crust. And that's a fact. Apparently, if Mars were 5 to 9 times larger than it is now, the fourth planet in our system would be habitable. Observations of other planetary systems show Earth-sized planets, with Venus, Mars, and Mercury, being extremely rare. In other planetary systems, the mass of rocky worlds is usually much greater than Earth's. That's why they're called superpowers. Does it turn out that all of our Earth group planets are anomalies of some kind? Astronomers Michael Brown and Konstantin Batygin believe, and most of the world's scientists agree with them, that there is a super-Earth in the solar system. It is simply incredibly distant from the Sun, hundreds of times farther than Earth and 10 times farther than Neptune. Of course, protoplanetary disks of this size have never existed in our system. In other words, this super-Earth got there by exotic means after it formed near the Sun. In other systems, such an event as the movement of planets to or from their star is a strange phenomenon. A whole class of planets called hot Jupiters exist only because of the wandering of their stars. The Sun doesn't have any. Gas planets cannot appear near stars. However, once formed, the gas giant may lose its orbital stability. It can collide with Earth group planets, gradually slowing its rotation around its star. As the speed of rotation decreases, the planet begins to describe increasingly narrow circles around its star. At the same time, its gravity ejects objects it encounters on its way out of the system. Therefore, hot Jupiters often leave their star without Earth group planets, and they themselves come so close to it that they heat up to thousands of degrees. A clear picture emerges from such a scenario. Our system was also originally quite different. Giant planets were not necessarily born where they are today. Astronomers have created some fairly detailed mathematical models of the motion of solar system bodies and discovered something unexpected. From the point of view of celestial mechanics, the original region of Jupiter's formation, which would correspond to its present orbital elongation and position, is only 3.5 AU from the Sun, or 3.5 times the present distance between Earth and the star. However, Jupiter is currently at an average distance of 5.2 AU from the Sun, which is 250 million kilometers. But how did it get there? This is where computer modeling comes in. Collisions with the Earth slowed down Jupiter's rotation around the Sun, causing the planet to move more slowly along its orbit and thus begin to approach it. On its way to the Sun, Jupiter's gravity dragged Saturn along with it. Earth group planets form more slowly than the gas giants and stop forming after them. So, Earth and Mars are lucky in a way. If they had already existed then, they would have been in great danger. Jupiter stopped just 1.5 astronomical units from the Sun, so it was a little closer to Mars. The formed planets would have gotten too much momentum from their gravity, and their orbits would have been too unstable. Most likely, they'll just fly out of the system. However, the transit of Jupiter brought serious problems to the future rocky planets. Its gravity did its job. The gas and dust from this part of the protoplanetary disk was literally swallowed up by Jupiter. He had to eject part of the planet Zemlya out of the system. The region where Mars formed was so poor in material that it received far less material than Earth. But why did Jupiter not stay within an AU and a half of the Sun, but turned around and went back? There's only one explanation. Moving behind Jupiter, Saturn entered a resonant orbit with Jupiter at a certain point. That means that the period of 2 revolutions of Saturn around the Sun was equal to 3 revolutions of Jupiter. 3-to-2 resonance. Orbital resonance means that bodies regularly encounter each other. The gravitational interaction between the two is dramatically increasing, and their orbits are undergoing major changes. The connection with Saturn pulled Jupiter back in time. After all, what would happen if the largest gas giant did not stop at a distance of 1.5 astronomical units, but reached one? You mean up to Earth's orbit? Maybe in that case there would be no one to ask. Earth will be as small a planet as Mars because Jupiter's transit won't leave much material to form it. Even if it had life on it, it is unlikely to have been as advanced as it is today. It is believed that Jupiter is the patron saint of the Earth. Today it protects our planet from asteroid impacts. In this case, Saturn is the savior of the Earth. Such a journey of Jupiter could not help but affect Uranus and Neptune. At first, they were less than 17 AU away from the Sun. The wandering of Jupiter and Saturn finally threw them into distant orbits. They remain there to this day. Uranus shown at mid-19 AU and Neptune at 30. And what about the super-Earths of the solar system? They're the most massive class of planets in the Milky Way, but they're not in our system. They form faster than the smaller Earth group bodies, so when Jupiter's migration begins, they could already be in our system. In that case, they were in for an enviable fate. They should have been destroyed by falling into the Sun. In the rocky planetary regions of the solar system, the remaining material of the protoplanetary disk was too small to form a second-generation super-Earth. In all, it took the formation of 4 planets with masses about half that of Earth. But it's not all smooth sailing. Almost all computer simulations of early solar system transitions show that its current configuration afterward is unlikely. At best, the planets should be in different orbits with slightly different elongations. They understood this problem for a long time, until they tried to include more planets in the modeling. It turns out that if the early solar system had not 4, as it does today, but 5 giant planets, the probability of the system forming in its current form increases significantly. In fact, about 4.6 billion years ago, there were almost certainly 5 such planets, and the 5th planet was an ice giant like Uranus or Neptune. In addition, astronomers Batygin and Brown, who have hypothesized a 9th planet orbiting at a distance of hundreds of astronomical units from the Sun, note that it is probably a large object, or one that was once flung there during the Great Jupiter voyage. Back. Thus, almost the entire architecture of the solar system was determined by events before the Earth existed. In place of Mercury, Venus, our planet, and Mars, there could be a super-Earth right now. Perhaps more than one. Back then, there were 5 giant planets, not 4. The chaotic migration of Jupiter and Saturn destroyed all the ancient super-Earths, ejecting them into the Sun, and simultaneously ejected the 9th planet of the present solar system. At the same time, Jupiter and Saturn themselves have moved farther away from the Sun, and Uranus and Neptune even farther from the light. It turns out that the migration of giant planets is the main mechanism governing the scenario of planetary system evolution. Those with hot Jupiter can usually lose Earth group planets and habitability. Their giant planets are so hot because their journey ended close to their star. They had no Saturn of their own to turn them around. The continued presence of giant planets in near-stellar orbits makes it less likely that a smaller rocky planet will be in the habitable zone. But there are systems where the migration of giant planets has not occurred at all. In this case, they form a super-Earth in orbit near the star. The best-known such system is TROPIST-1, 40 light-years from Earth. It is not yet known how habitable they are, but if they are, such systems could have more than 1 and sometimes more than 2 habitable planets. Whether this is true or not, we'll be able to find out in the coming years thanks to the soon-to-be operational James Webb Telescope. Before the discovery of massive exoplanets, it was widely believed among scientists that the solar system was the most favorable place for the formation of Earth group planets and life. But today, knowing the great migration of Jupiter, this hypothesis no longer seems reasonable. Earth and Mars escaped destruction and were not miraculously ejected into interstellar space. It appears that habitability in our system has been unusually difficult, and the number of habitable planets here is much lower than would be expected in quieter systems.
Stars. The sight of the starry sky is mesmerizing. It seems that one can admire it endlessly. There are so many mysteries and riddles. But what are stars? What are space objects called? What are stars? Stars are large celestial bodies scattered in space. Some substances remain in them due to mutual attraction. Stars have high temperatures, so they emit light that can be seen by observers on Earth. Objects are heated so strongly that any substance, even metal, is in a gaseous state, and their combination is called plasma. Why stars glow? Everything depends on the temperature difference between the core and the surface. Inside a star, it can reach 10 million degrees or more. Because of this, thermonuclear reactions are constantly occurring in the cosmic object, turning some chemical elements into others. For example, hydrogen, which makes up most stars, turns into helium in their cores. Due to this, there is a brightness that can be seen by the inhabitants of the Earth. Interesting fact, a person can see the stars of 3 nearby galaxies in the sky: Andromeda, Triangle, and the Milky Way. Powerful telescopes are needed to observe distant space objects. Naming stars. People began to give names to individual cosmic bodies and constellations in ancient times. At that time, people imagined the sky as the abode of various mythical creatures, after which they were named. Most of them are still in use today. The names of the constellations of the northern and southern hemisphere are surprisingly different. Here rule not mythical creatures, but different parts of ships and sea creatures. The fact is that the scientists of the southern hemisphere were poorly known in the ancient world. Its active development began in the era of great geographical discoveries. It makes sense that many constellations of the southern hemisphere were first discovered by sailors, who named them according to their preferences. So appeared in the sky keel, stern, etc. Now scientists recognize 88 constellations. 12 of them belong to the zodiac. The brightest celestial body they have is designated by the Greek letter alpha, the next, beta, etc. Individual letters are designated by an alphanumeric abbreviation. In addition, celestial bodies are classified by color and size. For example, blue giants or brown dwarfs. Star formation. The birth of a star is the fusion of hydrogen and helium molecules into one cloud. It begins to rotate. Internal gravity appears. This fact accelerates the rotation. The outer space of the cloud gradually begins to resemble a disk and the inner space begins to resemble a spherical cluster. The temperature of the material increases, as does its density. This leads to the formation of a globular protostar. Over time, the pressure and heat increase to 1 million Oc. This leads to the fusion of atomic nuclei. At this point, a new star begins to shine. The celestial body is almost invisible to the observer's eye because it is surrounded by a powerful cloud of gas and dust. As a result of nuclear fusion, a certain amount of atomic mass is gradually converted into energy. All this time, the star is moving under the influence of various forces. They mostly revolve around galaxies or space objects with a strong gravitational field. Interesting fact, stars can be seen in space at any time of day because time there is not divided into day and night. Stellar evolution. All cosmic bodies have a certain cycle of development called evolution. The mass of stars has a great influence on this process. The heavier the object, the shorter its life cycle. Cosmic bodies with an intermediate mass, i.e., 5 to 8 times heavier than the Sun, emerge from a cloud that can be up to 100,000 light-years in size. When the temperature inside reaches 3,725 C, the nebula forms a protostar. When hydrogen fusion begins, it becomes an object of varying brightness. Due to compression under the influence of gravity, the expansion process is balanced. The star begins to gain energy from the synthesis of hydrogen in its core. The formation of the object takes about 10 million years. When all the hydrogen is converted into helium, the matter under gravity becomes the core, which heats up rapidly. The outer layers expand, which quickly cool down under the influence of the external environment. This is how the red giant is formed. Next, chemical processes with helium begin. When it is completely transformed into other matter, the nucleus expands its shell as the temperature rises. This leads to the formation of a white dwarf, which can reach temperatures of 100,000 C. The products needed for heating will eventually run out, so the object will gradually cool down. After a few billion years, it will become a black dwarf and cease to exist. Evolution happens fastest in high-mass stars. It takes between 10,000 and 100,000 years from the creation of an object to the end of its life cycle. At the beginning of life, they are characterized by high temperature, bright and large. The star has a deep blue color. Gradually, it becomes a red supergiant, in which carbon is actively transformed into heavy elements. An iron core is formed. It can be up to 6,000 kilometers wide. Its nuclear radiation cannot resist gravity. When the mass of the cosmic object is about 1.5 times the mass of the Sun, the core collapses. This leads to the formation of a supernova. As it collapses, its temperature rises to 10 billion Oc, causing iron to decay in nerve cells. In a second, the core shrinks to 10 kilometers in size. Then the explosion occurs. Then there are two ways things could happen. If the remaining core weighed less than 3 suns, it would become a neutron star. The object spins and emits radio pulses. If the nucleus were heavier than 3 solar masses, it would collapse completely and a black hole would form in its place. Low-mass stars are the slowest to form. The reality is that they will slowly use up their fuel reserves. Their lifespans range from 100 billion to trillion years, so such objects are not dead yet. After all, the age of the universe has been determined to be 13.7 billion years. Red dwarfs cannot fuse with anything but hydrogen. As a result, they can't grow. Such luminaries slowly cool down and eventually become black dwarfs, after which they end their lives. Interesting fact, the first map of the starry sky was made about 3,000 years ago. Characteristics of stars. People use certain characteristics to describe stars perfectly. Brilliance. This concept was introduced by Hipparchus in 125 BC. He counted groups of stars according to their apparent brightness. The first ones are the most visible, the sixth ones are the faintest. At that time, however, it was not yet known that the distances between the Earth and other cosmic objects distort the light coming from them. Therefore, they now include a term such as true brightness when describing stars. Color depends on the temperature of the object. There are stars of blue, red, yellow, and white colors. Each spatial object has only one color. However, due to the chemical processes occurring inside, flashes of different light spectrum appear on the surface. By studying these phenomena, scientists find out what elements a star contains. Surface temperature. This is measured in Kelvin, where 0 equals minus 273.15 C. Temperature is affected by brightness, color, and mass. Magnitude. The diameter of the Sun is usually assumed to be constant. Alpha Centauri has a stellar magnitude of 1.5. Larger objects are also included. Red supergiants are 1,000 times larger than the Sun. Magnitude affects the brightness of the star. Mass. The Sun is also standard here. Alpha Centauri is 1.8 versus. Weight affects the temperature. Magnetic field. Each star is surrounded by a strong magnetic field. It is able to focus on certain areas of the target, causing flares and explosions. The faster a star rotates, the stronger the magnetic field around it. Metallicity. This indicator shows how many elements with a mass greater than helium the star contains. There are 3 generations of the metal. Scientists are still looking for the oldest 3, which has no heavy elements. Types. In addition to mass, size, etc., stars are divided into different types with unique properties. Main sequence stars. This indicator is based on the Hertzsprung-Russell diagram. In it, the stars are arranged diagonally. The brightest blue are in the upper left corner. The dim red one is in the lower right corner. Main sequence stars have the same nuclear reactions as their nuclei, namely the conversion of hydrogen to helium. The spectral class and temperature of a star depends on its mass measured relative to the Sun. Red giants and supergiants. The surface temperatures of these stars range from 3,000 to 500 K. However, they have a brighter glow. Helium is burned inside the object, which is then converted to carbon. Red and orange colored giants are located above the main stars in the Hertzsprung-Russell diagram. They are 100 to 800 times the diameter of the Sun, and in some cases YV Canis Majoris 1024 times the diameter of the Sun. White dwarfs. They represent the final stage of stellar evolution. These are essentially the nuclei of objects that have lost their outer shells due to expansion processes. They are small in size, 100 times smaller than the Sun, and low in luminosity, 10,000 times smaller, although they have almost the same mass as the Sun. The latter is due to the high density of the matter they contain. White dwarfs are clots of plasma with an electron core without energy sources. Their luminescence is due to the wear and tear of thermal reserves. Protostar. It is a cluster of gas formed after the collapse of a molecular cloud. It still cannot be called a full-fledged star. The development phase lasts about 100,000 years. Then gravity increases and the reservoir begins to collapse. The gas gradually builds up, releasing energy. This is where the rest of the star formation process begins. Brown dwarfs. Brown dwarfs are cosmic objects that are too big for planets but too small for stars. Their mass reaches 0. 8. Solar energy. Their formation process is similar to that of ordinary stars, but they lack the pressure and temperature to begin nuclear fusion. They contain light elements, boron, beryllium and lithium, deep within them. When the reactions between them stop, the object closes up and becomes a cosmic body like a planet. The possibility of the existence of brown dwarfs was proven long ago, but for a long time scientists could not observe them directly from space. The first such object was discovered in 2004 in the constellation Hydra. This is 2 meters 1207. Variable stars. Variable stars are objects whose luminosity index has changed one or more times. This may be due to internal processes and various other reasons. In the past, people considered changes in the light of space objects as supernatural. From a scientific point of view, attention was paid to this issue back in the 17th century. Since the 19th century, they have been categorized by their mechanisms of brightness change. Excitable variable stars are 2 nearby objects that sometimes cover each other from the Earth's point of view. Therefore, their brightness varies. Pulsating variable stars change their brightness due to the regular contraction and expansion of the cosmic object. This is because their gravity and internal pressure are unstable. During pulsation, the size of the emitting region changes, resulting in a change in brightness. Irregular variable stars have more complex causes of light pulsation. Science still doesn't know much about them. T-Taurus stars. This is the name given to objects that are an intermediate stage in the development of a protostar, when all of its energy is generated by the effects of gravity. They are not yet hot enough to start nuclear fusion. T-on-Taurus stars. Observers have observed gusts of wind, large spots, and bursts of X-rays. The duration of the processes is 100,000 years. Wolf-Rayet-type stars. Such stars are about 10 times larger than the Sun. They are characterized by high temperatures up to 50 K and brightness. Among other stars with similar characteristics, this type of luminosity is characterized by a special unique spectrum. The formation of Wolf-Rayet stars is still a matter of controversy. The most popular version is that they come from the helium remnants of large stars. At the moment, scientists have found 230 stars of this type. Interesting fact, on a clear night, a person can see up to 3,000 stars with the naked eye. Supernovae. Supernovae are objects in which an explosion has occurred as a result of evolutionary processes. This kind of phenomenon can be seen from a distance. For an observer on Earth, it looks like a strong and spontaneous amplification of starlight, which can last up to 10 days. Similar phenomena can be seen even during the day with the naked eye. Supernovae are distinguished from new stars by their explosive power. Neutron. If the mass of the star was less than 1/35 of the Sun, it will not become a white dwarf after the explosion, but will become a supernova. The result of this process is a nucleus. It is called a neutron star. This is due to the compression of protons and electrons under the influence of gravity. If the mass of the object was more than 3 times the mass of the Sun, a black hole will form at the site of the explosion. The radius of a neutron star rarely exceeds 20 kilometers. The object has a strong magnetic field, which is created due to its rapid rotation, 1,000 revolutions per minute. Double stars. It is a system of 2 stars that are gravitationally attracted to each other. Some objects not only revolve around each other, but also exchange the masses of their matter. About 50% of all stars in our galaxy belong to this type. Binary symbols are denoted by Latin letters. A is brighter and more massive. B is dim and bright. The structure of stars. In the universe, the stars are mostly in the main sequence stage and consist of a nucleus, corona, photosphere, and chromosphere. Thermonuclear reactions are constantly taking place in the subject's intestines. The resulting energy travels through the radiation zone. The force moves through convective regions due to burning gases. The photosphere of a star refers to its surface. This is the opaque part. Then comes the chromosphere, which has a reddish hue due to the presence of hydrogen. The corona is the outer sphere of the star. This part of the object has a high temperature and can be attached to the outer layers due to convection. Atmosphere radiation is produced in the star's atmosphere, which is visible to observers from Earth. It consists of 4 zones: the luminous and chromospheric zones, the rotating layer, and the corona. Many objects have a variable stellar wind. This is the name given to the process of the expulsion of substances contained in the atmosphere into space. The appearance of stellar wind indicates instability in the atmosphere. This phenomenon is strongest for high-mass objects. Classification. The first classification of stars was made by the Italian astronomer Angelo Secchi in 1863. He divided the luminaries into 4 spectral classes, to which, after further research, another one was added. There are now 8 of them. In addition, each category is divided into 10 types. It all depends on the surface temperature of the objects. According to the Morgan-Keenan system, mass and luminosity values are added to the above indicators. The largest star in the universe. Researchers at the Bonn Observatory discovered the largest star in the universe in 1860. However, it has only recently been fully studied. This is the star in the constellation Shields. Its radius is 1,700 times larger than the Sun. It is located at a distance of 9,500 light-years from Earth. If iSCUDdy was in the position of the Sun, it would have captured the first 5 planets and entered the orbit of Jupiter. Technological capabilities are improving every year. Perhaps in a few years people will find a new, larger star. The smallest star in the universe, the nearest star, is the red dwarf Proxima Centauri. Its size is modest to 12.3 times the mass of the Sun and 200 kilometers across. It is about half the size of Jupiter, but the structure of these objects is different. A star heavier than a planet. Proxima Centauri is very faint. You can see it in the sky only with the help of special equipment. Interesting fact, the smallest star visible to the naked eye is 61 Swan. Its mass is 66% of the mass of the Sun. Which star was the first? Scientists believe that the universe originated from the Big Bang 13.7 billion years ago. At first, the temperature in space was very high, which did not allow the formation of stars and other objects. After a few million years, it shrank. Gravitational forces began to pull hydrogen and helium together. Then it was time to achieve the perfect temperature and pressure ratio. Hydrogen began to synthesize into helium. Because of this, stars accumulated to a large mass up to 150 solar masses. That's how the first generation was born. After a few million years, most of them exploded. But during their existence, they managed to form heavy elements, which flew into outer space after their death. This, in turn, led to the formation of stars as people observe them today. Observational history. The starry sky has fascinated people since ancient times. At first it was given mythical properties, then mankind learned to use it for practical purposes. For many centuries, sailors from different countries steered their ships by the stars. People have always been curious. They wanted to study the starry sky, to understand the laws by which the stars move. Therefore, astronomy is considered one of the oldest sciences. Technological progress has not stopped. Telescopes and other necessary instruments appeared. In the 17th century, the law of gravitation and motion was discovered. Over time, people realized that many stars are similar to the Sun and, therefore, obey the same laws of physics. Photography and spectroscopy analysis of light waves coming from an object appeared in the 19th century. It allowed people to penetrate into the composition of the stars and understand the basic principles of the movement of the luminaries. In 1937, the first radio telescope was created, which allowed the study of radiation from stars. This allowed astronomers to better study the internal structure of space objects. 1990, the first Hubble Space Telescope was launched. This allowed scientists to study areas inaccessible to observers from Earth. Solar system. The Sun has a tremendous gravitational force that allows it to hold the planets close to it, forming the entire system. They orbit each other and have certain characteristics depending on their location. Scientists are constantly exploring the solar system and are constantly making incredible discoveries that help us better understand the structure of the cosmos. What is a solar system? The solar system is a collection of planets orbiting around a central star. Scientists have been able to determine that it is approximately 4.57 billion years old and was formed by the gravitational compression of a cloud of gas and dust. At the heart of the system is a bright star, the Sun, which contains planets and other objects. Make them rotate a certain distance. Its diameter is several times larger than other gravitational field objects. Interesting fact, the mass of the Sun is so great that all the other planets in the system are only 0.14% of its mass. In addition to the star, the solar system has 8 large planets and 5 dwarf planets. It is located in the Milky Way galaxy below Orion. Formation. Since the solar system is billions of years old, people can only speculate how it formed. The most popular is the fog theory, which was introduced by scientists Laplace, Kant and Swedenborg in the 18th century. It is based on the fact that the system was formed by the gravitational collapse of one part of a huge cloud of gas and dust. The hypothesis has since been supplemented by space exploration data. The process of formation of the solar system is now described by the following steps. 1. In the beginning, in this region of the universe was a cloud of helium, hydrogen, and other substances formed by explosions. Old stars in a small part of it began to compact, which became the center of gravitational collapse. Gradually, it began to attract the surrounding subjects. 2. Because of the attraction of matter, the size of the cloud began to decrease and the speed of rotation increased. Its shape gradually changed to a lamellar shape. 3. As compression increased, the density of particles per unit volume increased, causing the matter to gradually heat up due to repeated collisions between molecules. 4. When the collapsing center of gravity heated up to several thousand Kelvin, it began to glow, indicating the formation of a protostar. At the same time, other condensates began to form in different regions of the disk, which in the future would serve as centers of gravity for the formation of planets. 5. The final stage of solar system formation began when the temperature of the center of the protostar exceeded a few million kelvins. Helium and hydrogen then underwent a fusion reaction that led to the birth of the perfect star. The remaining compacts of the disk little by little formed planets that began orbiting the Sun in the same direction, being in the same plane. This process took a very long time, and scientists can only guess how many years it took for the solar system to form. Structure of the solar system. At the center of the solar system is the Sun, which is composed of helium and hydrogen. Its surface temperature is about 6,000 degrees Celsius, and the sphere is many times the size of other objects in its gravitational field. The star is a yellow dwarf. Interesting fact, the Sun attracts objects to light years away. It is about 18.9 trillion kilometers across. At different distances around the star are the planets, which scientists divide into two groups: terrestrial planets and gas planets. Earth group planets. The Earth group is closer to the Sun. Its planets have a rocky texture and high density, making them smaller than the gas giants. Mercury, the closest planet to the Sun, is also the smallest planet in the system. It has a radius of only 440 kilometers. It gets its name in honor of Mercury, the god of commerce. Its surface is gray, which is why many people compare it to the Moon. The planet has no satellites and is almost completely devoid of atmosphere by strong solar winds. Venus, the second planet from the Sun, is named after the ancient Roman goddess of love. The peculiarity is the absence of natural satellites and a high concentration of carbon dioxide in the atmosphere. The radius of Venus is almost identical to that of Earth, 6,051 kilometers, which is only 5% less. This is why the planets are called brothers and sisters. However, Venus is very different in appearance, as it resembles a milk bowl. The surface consists almost entirely of petrified lava with rare meteorite craters. Earth, the third planet from the Sun, the only one whose territorial areas are filled with water. Due to favorable climatic conditions and sufficient resources, it is the only source of life in the solar system. The planet has a radius of 6,378 kilometers. Mars, red planet, is the farthest from the Sun and belongs to the Earth group. It is also considered the smallest after Mercury. Its radius is 3,396 kilometers. Earth consists mainly of sandy and clay landforms that are divided into light and dark areas called continents and seas. Mars is of great interest to scientists in the 21st century. Since the planet is relatively accessible, Mars rovers are regularly sent out to collect data. Gas group planets. This group consists of 4 gas giants that are farther from the Sun than the other planets. Its huge size is due to its low density composition and large amount of gaseous matter. Jupiter, the largest planet in the solar system. It has a radius of 69,912 kilometers, which is almost 20 times the radius of Earth. Scientists still cannot determine the exact composition of the planet. They only know that it contains more xenon, argon, and krypton than the Sun. Jupiter also has 67 satellites, some of which look like planets. For example, Ganymede is 8% larger than Mercury, and Io has its own atmosphere. There is also a theory that Jupiter was meant to become a full-fledged star, but remained a planet during its developmental stage. Saturn, the 6th planet known for its icy rings and rock meteoroids. Saturn has a radius of 57,360 kilometers. Scientists have not yet studied in detail the composition of the surface, but were able to show that it contains almost the same chemical elements as the Sun. There are 62 satellites around Saturn. Interesting fact, rings have recently been discovered in other gas giants besides Saturn, but they are not so remarkable. The reasons for their appearance can only be speculated at this point. Uranus, the third largest planet in the solar system. It has a radius of 25,267 kilometers. Uranus has a temperature of minus 230 degrees Celsius, making it the coldest planet. It also has a unique feature. The axis of rotation is located at an angle, because of which the planet gives the impression of a rotating sphere when moving. The surface consists mostly of ice with small amounts of helium and hydrogen. Neptune, the eighth planet from the Sun, was discovered not by observation, but by mathematical calculations. Observing the anomalies in the motion of Uranus, scientists have suggested that they are caused by the presence of another large celestial body. Neptune has a radius of 24,547 kilometers. The surface is similar to uranium, but is driven by the system's strongest winds, accelerating up to 260 meters per second. Order of orbits: each planet has its own particular orbit in which it revolves around the Sun. The time it takes for it to return to the same point after coming full circle is called a year, most often measured in Earth days. Mercury is closest to the Sun, which makes it orbit the Sun in the smallest orbit, and it has a year of 88 days. Venus makes a complete revolution around its star in 224 days. For Earth, a year lasts 365 days. Mars takes almost twice as long to complete a full revolution as the third planet, 687 days. Jupiter, which is the nearest gaseous giant to the Sun, has a year's duration of 4,332 days. Saturn makes a complete revolution in 10,759 days. That's nearly 30 Earth years, being practically the farthest planet from the Sun. Uranus completes a circle in 30,685 days. Neptune has the largest orbit and has to travel the greatest distance during its year, which lasts 60,190 days, almost 165 years. Also, each planet rotates around its axis at a certain speed, which makes the length of the day on them different. Is Pluto part of the solar system or not? Since the 19th century, scientists have hypothesized that there is a ninth planet in the solar system that is farthest from the Sun. In 1930, 23-year-old Clyde Tombaugh, an employee of the Mount Wilson Observatory, succeeded in finding Pluto. He did this by regularly photographing the starry sky and looking for moving elements. The object was found in the Kuiper Belt region. In the same year, Pluto was officially declared the ninth planet. Due to a lack of data, it was compared in size to Earth, but further research revealed that it had a radius of only 376 kilometers and a mass 6 times smaller than that of the Moon. The planet's surface consists mostly of rocks and ice. Like most Kuiper Belt objects, Pluto has 5 satellites. The orbit around the Sun has an oval shape, and at maximum approach the planet is closer to the light than Neptune, and at its greatest distance the distance is 7.4 billion kilometers. During further studies of the Kuiper Belt, scientists found several other small planets, the size of which is not much different from Pluto. In 2006, it was decided to dwarf them. Pluto has since officially ceased to be the ninth planet in the solar system. However, some scientists still insist that it should be moved back from dwarf to major. Other objects: in addition to the Sun and planets, there are other objects in the system. These include dwarf planets that are inferior in size to the major planets. Kuiper Belt, a disc-shaped region containing many icy bodies. Located beyond the orbit of Neptune. Oort cloud, a cluster of icy conglomerates. Comets, formations of gas, dust, and ice moving through space. Asteroids, rock formations traveling between Mars and Jupiter. Meteorites, small solid objects that fall to the Earth, turn into meteors when they hit the atmosphere, and burn up before reaching the planet's surface. Sometimes asteroids and comets from neighboring galaxies can fly into the solar system, but this phenomenon is quite rare. The Oort cloud is outside the solar system. The Oort cloud is located around the solar system and the Kuiper Belt. Its inner limits begin at 200 to 500 U. Its distance from the Sun and outward is 100 to 200 U. To facilitate study, researchers divide the region into outer and inner parts. The cloud is made up of trillions of particles consisting of ethane, water, methane, ammonia, hydrogen, and other substances. Among them there are rocky asteroids, which make up 2% of the total number of objects. Almost all bodies are less than a kilometer in diameter, with dwarf planets being a rare exception. Interplanetary space, many people think that there is nothing between the planets. However, this assumption is incorrect. The Sun constantly emits charged particles that travel through space at 1.5 million kilometers per hour and form the heliosphere. This current is called the solar wind. If an object doesn't have its own magnetic field holding back the atmosphere, the charged particles will literally tear it apart. A similar fate befell Mars and Venus. Colonization in the 20th century, space was actively explored not only by observing it in a telescope, but also with the help of various satellites, shuttles, rockets, etc. For life, unfortunately, a cataclysm may occur on Earth at any moment, so mankind needs to find a new home. Therefore, the possible colonization of space is not an empty sound for modern observatories. In the last century, probes have been sent to various planets and have continued to relay information about their journey. This helps to better understand the structure and properties of objects of the solar system. As for direct colonization, sending Mars rovers to circle the surface of the Earth's satellite and the fourth planet in search of life and other unusual discoveries is already the order of the 21st century. However, now humanity is only on the threshold of space travel, so it is not necessary to talk about a possible flight to another planet. Moreover, most of the large bodies of the solar system are unsuitable for life. Why the solar system is stable, all the planets revolve around the Sun in their orbits, without touching each other in any way. They are also constantly affected by the attraction of the stars, which is based on the law of universal gravitation. And since there is no friction in space, the planets move at a constant speed, and for billions of years the solar system has enjoyed enviable stability. Earth's place in the solar system can be called the most favorable, since life originated on this planet. The third planet revolves around the star on ellipsoids. The maximum distance between the Earth and the Sun is 152 million kilometers and is called aphelion, and the minimum distance is 147 million kilometers and is called perigee. An interesting fact is that while traveling, the Earth reaches aphelion in June and perigee in January. At the intersection of these points, the planet begins to experience a steady cooling or warming. Due to its favorable location, the Earth is constantly warmed by the Sun's rays. Depending on the season and location, the surface temperature varies from -89 to 57 degrees Celsius. This is sufficient for the origin and development of life. The solar system's place in the galaxy. In the Middle Ages, it was believed that the Earth was the center of the universe. Since it was impossible to estimate the size of the room at the time, this assumption seemed the most logical. It was later discovered that the planet is just a part of the solar system centered in a giant star. And even later, it became known that this is only a part of a large galaxy, the Milky Way, which, in turn, is one of many in the universe. Scientists have created a global map of the Milky Way. It encompasses all known boundaries and has a total width of about 100 light-years. For convenience, the galaxy is represented as a flat disk. The solar system is located almost sideways, 28,000 light-years away from the center. Exploration of the solar system. Since the middle of the 20th century, people have been actively trying to explore the planets of the solar system. In 1957, the Soviet Union launched Sputnik 1 into Earth orbit. He spent several months in space gathering information about the planet. Over the next 2 decades, up until the 1980s, people sent travelers to most of the planets in the system, taking many close-up photographs. This helped to create detailed descriptions of objects and study composition. Now every day scientists receive a lot of information about the planets of the solar system, which is transmitted by dozens of satellites. Why do the orbits of the planets lie in the same plane? In the solar system, the star and planets are on the same level. Only a few orbits are slightly tilted. Scientists believe this is because the objects formed at the same time and from the same material. During the collapse of the galaxy when the solar system was born, the gas cloud gradually narrowed and turned into a rotating disk. Therefore, when the planets of the future began to turn into condensation, they were already at the same level. The motion of the planets around the Sun. The ancient Greek astronomer Ptolemy was the first to suggest that the planets and the Sun do not remain stationary, but rotate in their orbits. However, due to lack of technology and knowledge, scientists believed that all objects revolved around the Earth. Nicolaus Copernicus hypothesized that the planets revolved around the sun. He built his own model of the solar system and, on its basis, wrote the rotation of the celestial balls. The work was published in 1543 in Nuremberg. Sometime later, Kepler showed that the orbits of the planets are not circular but ellipsoidal. In 1687, Newton discovered the universal law of gravitation, which explained the interaction between the planets and the sun. Interesting fact: Newton's law helped to prove that the tides on Earth are caused by the activity of the moon. Now people have enough knowledge and technology to predict the exact trajectory of any planet. Based on this information, rockets and satellites are launched to meet the target at a certain point in space and after a certain time.